Hands-on project, predicting diabetes with Ensemble models. Welcome to our data mining project for beginners. This week, we will predict whether someone has diabetes using a real medical dataset. We will use the Pima Indians Diabetes dataset from the UCI Machine Learning repository. Throughout this lesson, you will learn how to clean data, explore patterns, build predictive models, and combine multiple models for better results. Let us get started. Running the cell now. After this cell, can you describe what you expect this project will do? Let us load the dataset and see what it looks like. We import the warnings module to turn off warning messages. We set up our script to ignore warnings, so we have a clean output. We are loading the Pima Indians Diabetes dataset using pandas. We add column names to make it easy to read and use. Import NumPy as NP. We set the random seed to 42 for reproducibility. We now use pandas to load the CSV from its URL and give the columns real names. We define a list of column names matching the dataset features and target. We read the CSV data into a pandas data frame with the specified column names. We print the shape of a data frame to see how many rows and columns it has. We print the first 3 rows of the data frame to preview the data. Running the cell now. Here we load the Pima Indians Diabetes dataset, which contains 768 patient records and 9 columns including features like glucose and BMI, plus the target column outcome indicating diabetes presence, 1 or 0. Noticing the data shape and preview helps us confirm successful loading and understand the key variables we'll use for prediction in this project. Can you spot which features are measurements and which is the label? Let us get familiar with the columns. Understanding the features. Here are the columns in our dataset. Pregnancies, number of times pregnant. Glucose, plasma glucose concentration. Blood pressure, diastolic blood pressure. Skin thickness, skin fold thickness. Insulin, 2-hour serum insulin. BMI, body mass index. Diabetes pedigree function. Age in years. Outcome, 1 if diabetic, 0 otherwise. Outcome is our target variable. We will predict it using the other columns. Running the cell now. Which feature do you think might matter the most? Before using the data, we need to check for missing or odd values. Comment: checking your data's quality is important because missing or odd values can mislead our model. We check for standard missing values with pandas. We display how many missing values are in each column. For health datasets, zeros may mean information is missing instead of it being real. We count zeros in every column to check for possible missingness. Running the cell now. This output shows that there are no missing values in any columns, but several features contain 0 values, which may represent missing or invalid data, especially in health-related columns like glucose, blood pressure, and insulin. Notice the high 0 counts in insulin and skin thickness, indicating we need to handle these carefully before analysis. This code helps us assess data quality and informs the next steps in pre-processing these important features. Look at these results. Which columns have the most zeros? How might this affect your model? Zeros in columns like glucose usually mean values were not measured, not that the result was actually 0. We add a comment to explain that zeros in certain columns will be replaced with nan, except for pregnancies and outcome. We import the NumPy library to handle numeric operations such as representing missing values with nan. We specify the columns where zeros are considered invalid and should be treated as missing data. We replace all zeros in the specified columns with nan to mark them as missing values. We print the count of missing values in each column to see how many nans were introduced. Running the cell now. This output shows the count of missing values after replacing zeros with nan in specific columns, highlighting that some features like blood pressure and insulin have many missing entries. Notice how pregnancies and outcome have 0 missing values, confirming they were excluded from replacement as intended. This step is crucial for understanding data quality and preparing for accurate analysis or imputation in later lessons. Practice: why do we not replace zeros in pregnancies or outcome? Now, let us fill in the missing values so models will not break. We fill in each missing number with the median of its column. The median is the middle value, and it helps avoid bias from outliers. We do this in place, so it updates our original data. We check again. Now, there should be no missing values left. Running the cell now. This output shows that there are no missing values left in any columns after filling them with their median values. Notice how each feature, including key ones like glucose and blood pressure, now has 0 null counts, ensuring clean and complete data for analysis. This step is essential for accurate modeling and understanding of the dataset's features without data gaps. Can you think of other ways to fill missing values besides the median? Let us get a summary of the statistics for each measurement. We use pandas to show basic descriptive statistics for all columns. This helps us understand their ranges, means, and typical values. Running the cell now. This output shows basic statistics for each feature, helping us understand their typical values and ranges. Notably, that pregnancies count ranges from 0 to 17 with a mean around 3.8, while the glucose averages about 122 but spans a wide range up to 199, indicating variability in our data. Reviewing these stats confirms the dataset structure and helps us anticipate which features might influence our analysis the most. Which features seem to have the widest range? Let us see how each feature is spread out using histograms. We add a comment to explain that we are visualizing feature distributions using histograms. We import the matplotlib library for creating plots. We create histograms for each feature in the data frame to show their value distributions. We add an overall title to the histogram plot. We adjust the plot layout to prevent overlap and make it look neat. We display the completed plot on the screen. Running the cell now. The histograms show the distribution of each feature in our dataset, such as pregnancies, glucose, and blood pressure. Notice the varying shapes. Some features are skewed while others are more normally distributed, which helps us understand the data's range and common values before modeling. This visualization confirms key characteristics of each feature, guiding decisions on pre-processing and feature engineering. Choose a feature. How is its distribution shaped? Is it skewed or more centered? Now, let us look for relationships between features using a correlation heatmap. We comment that we will visualize correlations in the data. We import Seaborn, a library for more attractive plots. We set the plot size with matplotlib. We calculate the correlation between all pairs of columns, showing how closely they are related. We ask Seaborn to draw a heat map. Annotating the numbers helps us spot strong links. We add a helpful title to the plot. Finally, we display the heat map. Running the cell now. This heat map shows the correlation coefficients between all pairs of features in our dataset, with values close to 1 or -1 indicating strong positive or negative relationships. Notice which columns, like glucose, might have stronger correlations with others, helping us understand which features are most related and potentially important for our analysis or modeling. This visual summary connects to our intent of grasping feature relationships to guide feature selection. Which feature is most strongly associated with the label outcome? Training and testing data help us avoid misleading ourselves. Splitting the data for learning. We need separate training and test data. This lets us build models on one part and check accuracy on another. Let us split the data into inputs, called X, and labels, called Y. Then we will break them into train and test sets. Running the cell now. Why is it important to have a test set when you build a model? Let us organize our data for the modeling step. We put all features except outcome into X. The outcome column goes into Y as our label. We assign the label column for outcome to Y for prediction. We import the train_test_split function from scikit-learn. We split the data with 80% for training and 20% for testing, and set a random state to make results repeatable. We print the number of training samples. We print the number of testing samples. Running the cell now. The output shows the number of samples allocated to the training set, 614, and the test set, 154, confirming the 80/20th split specified in the code. This balance is important because it ensures we have enough data to train the model while reserving a meaningful portion for evaluating its performance on unseen data. If our dataset had only 100 examples, how should we adjust the split? Before building fancy models, let us see how well we can do by guessing the most common label every time. We check which class appears the most in our training data. We find the most frequent class label in y_train. We import accuracy_score to compare predictions to correct answers. We make a prediction list that always guesses the most common value. We calculate the accuracy of this simple baseline. We print out the baseline accuracy so we know what to beat. Running the cell now. This output shows the baseline accuracy of always predicting the most common class from the training labels. Notice that the accuracy is about 64%, meaning that if we did nothing but guess the majority class, we'd be right roughly 2/3 of the time. This baseline sets a minimum benchmark to improve on when building more complex models with the split training and test data. Why is it helpful to build a simple baseline first? Let us fit our first real classifier, a decision tree. We try using a decision tree classifier as our model. We import the decision tree classifier from scikit-learn. We create a decision tree object with a fixed random state for reproducibility. We train the decision tree using the training data. We use the train tree to predict the labels for the test data. We calculate the accuracy of the predictions on the test set. We print out the accuracy score of the decision tree model. Running the cell now. This output shows the accuracy of a decision tree model trained on the training set and tested on the separate test set, achieving about 72% accuracy. Notice how splitting the data and using unseen test data allows us to evaluate the model's real performance, reflecting how well it generalizes beyond the training examples. This step is crucial for validating that our model isn't just memorizing but truly learning patterns. Notice, is this result better than baseline? What could help improve the tree? Now, let us try a random forest. It builds many trees and votes for an answer. Try using a random forest, which is an ensemble method combining many trees. We import the random forest classifier from scikit-learn's Ensemble module. We create a random forest model with 100 trees and set a random state for reproducibility. We train the random forest model on the training data, features and labels. We use the trained forest to predict labels for the test set. We calculate the accuracy by comparing the predicted labels to the true test labels. We print out the accuracy of the random forest model. It usually performs better than a single decision tree. Running the cell now. The output shows the accuracy of the random forest model on the test set, which is about 74.7%. This indicates how well the model, trained on the training data, generalizes to unseen data, highlighting the importance of splitting data into training and test sets to fairly evaluate model performance. Why might combining trees help compared to just using one? Gradient boosting is another type of ensemble. It builds trees that fix errors in previous trees. This line is a comment introducing gradient boosting as an ensemble method. We import gradient boosting classifier from scikit-learn. We create a boosting model and set a random state for repeatability. We train the boosting model using the training data. We use the trained model to predict the labels of the test set. We calculate the accuracy score by comparing test labels to predictions. We print the accuracy score of the gradient boosting model. Running the cell now. This output shows the accuracy of a gradient boosting model on the test set, achieving about 76%. It confirms that after splitting the data into training and test sets, the model can be trained on one portion, x_train, y_train, and evaluated on unseen data, x_test, y_test, to get a realistic measure of performance. Notice how this step validates the model's ability to generalize, which is essential for reliable predictions. How do random forests and boosting differ in how they use the trees? Let us combine all three models with a voting classifier. It averages their predictions for a final answer. This comment indicates we are combining three models using a voting classifier. We import voting classifier from scikit-learn. It lets us blend multiple classifiers' predictions. We create a voting classifier with our tree, forest, and boosting models. Soft voting considers each model's confidence. We fit the voting model to the training set. We predict labels on our test data using this ensemble. We compute the voting ensemble's accuracy. We print the accuracy for our ultimate ensemble. Running the cell now. This output shows the accuracy of a voting classifier, which combines three models to improve predictions. Notice the accuracy around 0.73, indicating that the ensemble approach performs reasonably well on the test set split earlier. This confirms that combining models can leverage their strengths when evaluated on unseen data, aligning with our goal to validate model performance after splitting the data. If one model is much better than the others, will voting always help? Why or why not? Let us compare the accuracy scores for each approach we tried. We show all model results with printed accuracy values. We print the accuracy for the baseline guesser. We print the accuracy for the decision tree. We print the accuracy for the random forest. We print accuracy for gradient boosting. We print accuracy for the voting ensemble. Running the cell now. The output shows accuracy scores for different models evaluated on the test data after splitting. Notice how each model improves on the baseline accuracy of 64.29%, demonstrating the value of splitting data for unbiased evaluation and comparing various algorithms. This confirms that splitting into trainer test sets provides a reliable way to measure real-world performance. Which method gives the best results? What are some reasons why? Let us pause to summarize what matters most for model building. Best practices and troubleshooting tips. Always check for missing or suspicious values. Use simple models first as a baseline. Ensemble models can improve performance, but sometimes add complexity. Evaluate models using a separate test set. If your model performs poorly, check for data errors. Experiment with more data or different model settings. Try smarter feature engineering. Remember, real-world projects are rarely perfect from the start. Running the cell now. What question would you ask when faced with a poor result? Try predicting on a new case, make up your own measurements and see what the model says. This is an extra practice section for predicting with your own input. We import NumPy to help us create and manipulate arrays. We create a NumPy array containing feature values for one example person. We use the voting classifier to predict the label for this example. We convert the numeric prediction into a readable label, diabetic or not diabetic. We print the prediction result in a human-friendly format. Running the cell now. This output shows the prediction for a custom input sample using the ensemble voting model. Notice the straightforward result, not diabetic, reflecting the model's binary classification based on the provided feature values. This step highlights the importance of testing your final model with new, real-world data to confirm its practical usability. Practice, change some numbers in the example and predict again. How sensitive is the result? Ready for a challenge? Try k-nearest neighbors, a classifier that looks at similar past rows. This line is a challenge prompt to try a different classifier. We import kNeighbors classifier from scikit-learn. We create a kNearest neighbors classifier with default settings. We fit it to our training data. We measure how accurate it is on the test set. We print out this new model's accuracy. Compare it to our earlier models. Running the cell now. Here, we see the kNearest neighbors classifier achieves about 67.5% accuracy on the test set, which serves as a new baseline to compare against previous models. Notice that this simple model's performance helps us evaluate whether more complex or ensemble methods are justified, reinforcing the lesson's point about starting with straightforward models and using test data for honest assessment. How does kNearest neighbors do versus trees and forests? Let us wrap up and review what we have learned. Recap what you learned. How to load and clean real-world medical data. Basics of splitting training and test data. Building, comparing, and combining machine learning models. How ensemble learning can improve predictions. Keep practicing and do not get discouraged. Each project brings new lessons. Running the cell now. Would you like to try building a model for a different dataset next? Thank you for learning with us today. Thanks for learning next steps. If you found this project helpful, please like and subscribe to our channel for more beginner-friendly tutorials. Try running the notebook again with small changes. What else can you discover? Happy coding! Running the cell now. Like and subscribe to see more beginner-friendly projects on YouTube.